Besides, we provide an interactive interface for the user to manually crop photos inside or outside the image according to both the user's visual preferences and the optimal view computed by our algorithm.
Light has temporal, spatial, and polarimetric properties. While polarization has often been ignored in graphics, animal vision systems have made great use of it. We analyze how light polarization changes with space and time, based on our novel 7-dimensional tensor model of light transport. This enables applications such as spatial and temporal decomposition, shape reconstruction, descattering, breaking metamerism, and birefringent analysis.
Many historical people make great contributions to the world. Unfortunately, we can only learn their appearance through these blurry, grainy black and white images. Have you ever wondered what they really look like? What if we can go back in time with a modern camera and take a new photo for them? We call it time travel photography. While it's impossible to realize physically, we want to simulate this computationally. Want to see how we rephotographed Abraham Lincoln, Marie Curie, Thomas Edison, and many more? Come to check out our talk to find out more.
How can you scan this complex object? A single viewpoint is not enough for full surround coverage. A multi-view projector camera system is hard to build. Instead, we put the object in a kaleidoscope. This is equivalent to a virtual multi-view system. Our pipeline is, we scan the object and label the virtual viewpoint of each pixel. Now this is equivalent to a light stage with hundreds of virtual projectors and cameras, so we can reconstruct a point cloud and a mesh. To see more scanned shapes, please come to our talk.
We present Barbershop, an effective and robust solution to hairstyle transfer using GAN-based image compositing with segmentation masks. Have you ever wondered what you would look like with another person's hairstyle? With Barbershop, you can transfer hairstyles from other portrait images. We can transfer the hair texture and color, or we can completely transfer the hairstyle. We can mix the overall shape, structure, and style from different images. Please watch our presentation for more information.
Is it easy to design realistic hairstyles via sketching even for novices? Yes. Our proposed system, Sketch Hair Salon, is able to create desired hairstyle images from scratch only by drawing several strokes. We use colored strokes to control the geometry and appearance independently during designing. Our system supports diverse hairstyles, including straight, wavy, braided, and their combinations.
We present EyelashNet, the first eyelash matting dataset generated by a specifically designed fluorescent labeling system. By coloring the eyelashes with a safe and invisible fluorescent substance, our system takes paired photos with colored and normal eyelashes by turning the ultraviolet flash on and off. We further use a novel alpha matte inference network to extract the eyelash alpha matte from the paired eyelash photos. Based on the dataset, we train a baseline matting network to estimate high-quality eyelash alpha mattes from portrait images. The eyelash matting enables us to remove the interference of eyelashes in the high-fidelity avatar reconstruction pipeline. For more details about eyelash matting, please come to our talk.
We present Pose with Style for re-rendering a person from a single image under arbitrary poses. Our method synthesizes occluded contents photorealistically while preserving the identity and fine details in the source image. To handle large pose changes, we embed the correspondence field, between the body surface texture and the source image with a human body symmetry prior. This allows us to warp from the source to the target view. To generate photorealistic results, we extend StyleGAN generator and introduce a spatially varying modulation of the latent space using warp local features from the source image. We can also achieve virtual try-on by combining warp source features from multiple image sources.
Wanna dance like a professional dancer but not good at dancing? Try our method, New Actor. Trained on multi-view videos of a person, New Actor can synthesize video realistic animations of the person under pose control. We can freely change a viewpoint for rendering. New Actor generalizes well to novel and challenging poses. Note the pose-dependent deformations and pose and view-dependent dynamic appearance effects in the results. New Actor enables visual effects such as synchronized crowd dancing. Join our talk for more details.
We present live speech portraits, a method for photorealistic talking head animation. Given an arbitrary input audio stream, our method can generate expressive and photorealistic animation of a target person in real time. We first generate facial dynamics, head poses, and upper body motions from audio, and then synthesize the facial images from these predictions.
Story of the game, really. They stepped on from there, and we couldn't get ourselves going. And in fact, we went away from our game plan and started forcing things.
Are you the one with the next big idea in face reconstruction, tracking, or relighting? Are you looking for ways to make your synthetic data look photoreal to train your neural network? Then our new work, Rendering with Style, may be just what you're looking for. We present a hybrid rendering technique that combines traditional rendering with a pre-trained generative model to consistently lift partial renders of a face to photoreal full-head portraits, complete with hair and eyes. Our technique can process simple animations, challenging lighting conditions, and even lets you generate an infinite variety of realistic examples for the same subject. Interested? Then we invite you to our talk for more details.
Generative models such as StyleGAN have reached photorealism for portrait rendering. An informed manipulation of latent codes allows changing the face pose, but the range of obtainable poses is severely limited. We introduced the camera manifold. It captures the space of physically meaningful cameras that StyleGAN can reproduce. This enables free viewpoint portrait rendering. Our precise camera control allows to insert StyleGAN renderings into synthetic scenes while maintaining all semantic editing capabilities of the model. And by the way, it can also lift StyleGAN renderings to stereo 3D.
To best accomplish large-scale urban scene acquisition using drones, we need to optimize for two goals: maximizing reconstruction quality while minimizing flight time. We introduce a path-oriented drone trajectory planning algorithm, which performs continuous image acquisition along an aerial path. Given a rough proxy, we build a view information field to enable an RRT expansion by simultaneously sampling viewpoints and optimizing trajectory. Our continuous path promotes high-fidelity details with much less on-site drone acquisition cost. For more information, welcome to our talk.
We introduce an on-the-fly aerial path planning system that enables a drone to capture an unknown environment. The drone explores the scene without any prior and follows an online-generated collision-free trajectory to collect scene data simultaneously. Given the 2D site boundary, our algorithm explores the scene by dividing the region and detecting interesting targets, resulting in high-quality data capturing in real time. Compared with offline SOTA methods, our online approach achieves decent reconstruction while largely reducing drone acquisition cost.
Do you spend a third of your day making mates? Then you may be a mechanical CAD designer. Specifying how parts connect and move in an assembly is such a chore. You need precision and expertise since these aren't meshes, they're
parametric boundary representations.
You need Automate, the neural network solution to your mating problems. Automate runs on SBGCN, the new graph network that embeds topologies of any dimension. What's that? How will you train this? Well, I hope you like big data, because Automate comes with over 500,000 mates. Over 500,000! That's a lot of mates! You can download the Automate dataset today for the low price of free. Automate suggests auto-completions to cat mates. SBGCN can embed BREFs for more than just mating. For more details, please watch our presentation.
A workspace and a work plan are essential for facilitating human collaboration to achieve production goals. For example, fast food restaurants' efficient production benefits from a streamlined workspace and an efficient work arrangement. Our approach consists of two major components, a workspace optimization and a work plan optimization. Our approach takes an empty workspace, equipment objects, staff properties, and a list of tasks as input. Then it optimizes the workspace and work plan alternatively until obtaining a satisfactory result. For more details about our joint optimization, please come to our talk.
Having difficulties finding ideal teleportation destinations manually in VR? Our scene perception-based VR teleportation approach automatically searches for visually desirable positions for you. Our approach learns and predicts visual desirability of positions in the input virtual scene, using scene perception graphs extracted from panoramic RGBD images. Considering the predicted desirability and other navigation properties, such as coverage and connectivity, our approach then synthesizes a teleport graph through an optimization procedure. Please come to our talk for more detail.
Have you ever wondered what makes trees look like trees? Well, we have. Typically, new tree generation techniques are assessed through limited user studies, which are expensive and difficult to implement. Introducing the IC-tree, an automatic metric estimating the perceived visual realism of botanical tree models in real time. First, we generated a diverse dataset of various tree models and scored them in a perceptual study with over 1 million pairwise comparisons. Next, we used the dataset to train two predictors, each estimating the visual realism of an input tree. Finally, we analyzed our data to find which properties determine trees' perceptual realism. Please attend our presentation for more details.
Nature produces strikingly beautiful patterns on flower petals. We've modeled them by combining interactive and simulation techniques. Monkey flower patterns are produced by reaction diffusion, which also produces patterns in calaria, and the orchid trichoglottis with anisotropic diffusion. Other simulations elaborate vein patterns in petals, or a random distribution of seed points. Please come to our talk on modeling flower pigmentation patterns.
This is what happens when we mix blue and yellow paint. We get green, it's a no-brainer. Yet, when we mix blue and yellow in painting software, we get gray. 30 years after pigment mixing has been introduced to computer graphics, and painting software still can't do it. This is even more painful when traditional media is simulated. We came up with a practical solution that can easily integrate pigment mixing into any existing painting software. If you're interested, come to our talk.
Lily's new skirt. Poor Lily only had one skirt, simple and plain. She envied other girls who was wearing delicacy and grace. One day she came across a frog. "I have magic," the frog said. "I'll give you the most beautiful skirt." The frog jumping, Lily's skirt sparkled colorfully. Lily mirrored herself by the water. Her reflection was wearing a brilliant skirt. "More choices!" The frog jumped. The skirt reflection turned to a new one. Lily was so happy to dance, her reflection dancing as well, wearing a refined skirt. Do you know how it happened? Please come to our talk. We'll reveal the magic.
In this paper, we present another approach to solve the rendering equation using neural networks. In this equation, L represents the solution, and we represent this solution using a single neural network. We then define a loss based on the norm of the difference between its left and right hand side, and we minimize it during training. Our approach has several advantages over existing techniques. For example, in an equal rendering time of 14 seconds, given a pre-trained network, we outperform path tracing in rendering novel views. Since our solution is view independent, we can produce novel views using the same neural network. Thanks for watching.
Given a set of images and their camera poses, neural radiance factorization, or NeurFactor, decomposes the appearance into 3D fields of surface normals, light visibility, albedo, and spatially varying BRDFs. With this factorization, we can relight the scene with a single point light, supporting shadows, or relight the scene with an arbitrary light probe. We achieve this by building upon NeurF and factorizing the observed radiance into reflectance and lighting. Please check out the project page for the paper, videos, code, and data.
Say you want to create a 3D scan of something in the real world just by waving your phone around. For example, maybe you want to scan yourself with a selfie video. Deformable neural radiance fields, such as NeurFs, can turn casual inputs like this one into photorealistic 3D representation. But whoa, what's this? Deformation-based models can't deal with changes in apparent topology, so NeurFs breaks if you make funny faces. We take inspiration from level set methods, modeling topologically varying shapes as cross-sections of a higher dimensional shape. Leveraging this perspective lets us model topologically varying scenes so you can make all the funny faces that you want. Please come see our talk for more details.
As Monte Carlo renderings can take up to hundreds of CPU core hours to render, wouldn't it be great to skip some of the frames and interpolate them instead? Unfortunately, the existing methods are not yet good enough with many visible artifacts. We present a method that uses auxiliary feature buffers of the missing frames that are very cheap to compute to guide interpolation. Our method significantly improves over the current state of the art and produces production level quality outputs. Come to our talk to learn more.
Holographic near-eye displays are an emerging technology promising a new generation of AR and VR systems. However, the image quality achieved by most holographic displays is low. This is mainly because of a model mismatch between the simulated wave propagation model and that is observed with the physical display. We introduce a new wave propagation model that leverages two neural networks on complex valued wave field that can be naturally extended to 3D setting. Our model is then trained to predict the holographic images using a camera focused on multiple target planes. With our trained model, we demonstrate a significantly better image quality compared to all other previous approaches with 2D and 3D, as well as VR and AR setups.
Today's computer graphics can produce photorealistic results, but can we make those so realistic that they are indistinguishable from real-world 3D scenes? To do this, we built a novel high dynamic range, multifocal stereo display with an end-to-end imaging and rendering system. The system can produce 3D objects with accurate color, contrast, disparity, and focal depth cues. This lets us reproduce virtual objects with such fidelity that they can be confused with real ones. Looking at these photographs, try to guess which of the objects are real and come to our presentation to find out.
What if you could talk to someone thousands of miles away, but see and hear them as if they were sitting directly across the table? In this work, we present a symmetric, real-time 3D communication system for one-on-one meetings, requiring no 3D glasses, head-mounted display, headphones, or body-worn microphones.
Participants demonstrate more engaged behaviors and a greater recall of meeting contents than when using traditional 2D video conferencing.
We can infer spatial information easily from video frames. However, we cannot infer it from mono audio. Therefore, to enhance the user experience, it's a good choice to convert the mono audio to binaural audio. Then we can judge the sound source according to the difference between the two channels. We present a learning-based approach for generating binaural audio using multitask learning, which combines two related tasks, the binaural audio generation task and the flipped audio classification task. Our approach can generate comparable or better results without introducing additional datasets.
Hi everyone, this is SIGGRAPH Asia. I'll be presenting VR social co-presence with light field displays. This is the idea right here. If you were in the same room with me, you'd see an auto-stereoscopic, perspective-correct view of my eyes, even though I'm wearing a VR headset. Watch our talk to hear more about the optical design of these displays, a pilot user study, and an easy-to-implement real-time light field renderer that we put together to run this hardware. See you there!
Artists use a stippling technique called inversion. They fill regions with dense black stipples to generate solid black color, leaving white gaps for negative space effects. In this paper, we mimic this technique by explicitly rendering the positive and negative space using black and white stipples. This allows us to stipple beautiful images that can preserve the structure and fine details in dark areas. Come to our talk to see cats, birds, and learn how to achieve this multi-class inverted stippling.
Line drawings convey the shape of an object by placing lines along edges and creases. We integrated line drawing into physically based rendering, allowing us to draw lines with glossy reflections, depth of field, and spectral dispersion, all physically simulated and seamlessly combined, opening up new avenues of creative expression for artists. To find out more, come see our talk on physically based feature line rendering.
Toon shading kind of sucks. It gives you these messy shadow shapes, and fixing it with normal smoothing just kills all the details. Mesh editing leaves you with static shading and flickery transitions. That's not at all how an artist would draw them by hand. Isn't there a better way to give toon shading that human touch? We propose to just let the damn human touch it. With Shading Rig, you can directly edit toon shading with our novel shading primitives. Then you can precisely define how shadows smoothly transition between light angles. Now games can dynamically correct the shading, allowing that human touch to be automatically preserved in real time. Watch our talk to see how we did it.
Virtual reality drawing applications let users draw 3D shapes with brushes that create ribbon-shaped strokes. Unfortunately, the geometries that can be drawn by existing ribbon brushes are limited. Drawing even medium complexity ribbons using these brushes requires users to employ unnatural wrist-twisting gestures. Our Adapt Brush method dramatically extends the space of ribbon geometries users can comfortably draw using purely translational controller motion by using an adaptive ruling computation mechanism. Our interface allows users to draw diverse, complex ribbons while only minimally changing the orientation of the controller and thus their wrist orientation. Come to our talk to learn more.
we introduced SKETCH-GNN, a convolutional graph neural network for semantic segmentation and labeling of freehand vector sketches. We treat an input stroke-based sketch as a graph with nodes representing the sampled points along input strokes and edges encoding the stroke structure information. To predict the per-node labels, our SKETCH-GNN uses graph convolution and a static dynamic branching network architecture to extract the features at 3 levels: point level, stroke level, and sketch level.
How do you represent a curve along a surface? You could store this curve as a polyline in space, but this relies essentially on floating point. Geometric topology provides us with a better way. All we have to do is count how many times the curve crosses each edge of the mesh. Amazingly, these counts alone allow us to reconstruct the curve exactly. This strategy works even on very complicated curves. Moreover, we can represent a whole new triangulation sitting along the mesh in the same way. We use this simple idea to build a robust data structure for intrinsic mesh processing. Our data structure allows us to robustly retriangulate low-quality meshes, which in turn greatly improves the robustness of downstream algorithms such as geodesic distance computation.
Higher-order polynomial patches are widely used in geometry processing, but computing core geometric operations, like this intersection, remains challenging on these patches. We provide a framework for computing many of these operations robustly and exactly. So we can solve problems like this one, where we want to prevent the teapot from colliding with the elephant. Plus we can compute some minimal bounding volumes to speed this up. We're able to robustly solve all of these problems and more using a powerful tool called sum of squares relaxation, which takes a hard-to-solve polynomial optimization problem and relaxes it into a convex problem, which can be solved efficiently. Come to our talk to learn more about the beautiful math behind SOS relaxation and how you can apply it to your own optimization problems.
Projective dynamics is a robust and efficient solver for real-time simulation, but it is hard to encode topological changes such as tearing and cutting. We propose a new algorithm for updating a Cholesky factorization which speeds up projective dynamic simulations with interactive cutting and tearing. Now, within the projective dynamics framework, a zombie can easily tear apart the t-shirt of an escapee. And a scalpel can cut apart tissues in a surgical simulation.
Inflating a tube using standard FEM and a high-Poisson ratio always leads to locking. With mixed FEM, we can alleviate the problem using the same tetrahedral mesh. We employed linear shape functions for both displacements and the pressures. For this cantilever beam, standard FEM completely locks. Our method allows us to more accurately simulate soft robots made of silicon rubber, which is modeled as a fully incompressible neo-Hookean material. Or we can squash a cat. Or even push it down the stairs.
Fluids and other animated visual effects data can follow complex paths with a wide range of non-rectangular shapes. We build upon a previous technique called fluid carving to provide a much more general, controllable, and efficient method for editing and post-processing such data. Our method allows users to enclose regions of interest in a lattice structure to intelligently resize them. Because our approach supports a wider range of data, more user control, and is orders of magnitude faster, it is more practical in production use cases. Please join our session to learn more.
Hex meshes are often preferred in numerical simulation over tetrahedral meshes for their reduced errors and fewer elements. Existing automatic hex meshing methods often suffer robustness issues and aren't aware of the user preference. We propose an interactive 4-stage pipeline where the user can reliably generate high-quality hex meshes and explore desirable trade-offs. Here's a demo of generating a hex mesh of the rocker arm using our system. Therefore, generating hex meshes can be as easy as playing Minecraft.
We present an algorithm to turn an adaptive grid into a conformal hexahedral mesh. State-of-the-art algorithms use octree properties to guarantee hexmeshability, but at the cost of an excessive over-refinement. We introduce a novel ILP approach that reduces the over-refinement required to make the grid hexmeshable by exploring a wider solution space. We always perform better or equal than the previous approaches in terms of elements number. If you are interested in our work, please come to our presentation.
In a quad mesh, you can do a collapse operation or a series of collapses. Conversely, you can do a split or series of splits. There are two types of collapses and two types of splits, neatly arranged as four actions corresponding to the four directions of compass. Transporting the compass along mesh editing, the operations can be read off the compass. Here's an example. This simple idea offers a zipper-like approach to edit singularities. Batches of our quad zipper, along with local smoothing, can beautify a quad mesh. That's QZip in a nutshell.
Volume meshing fills the interior of a surface with polyhedra. Unfortunately, many surface models have defects. Efficient meshing tools like TetGen may fail when the input has defects. Robust tools like TetWild work on any input, but they are extremely slow. The more recent FTetWild is much faster, but it is necessarily approximated. For the first time, we combine speed, exactness and robustness in one single tool. We enable robust editing tools that were non-feasible before, where exact Boolean operations can be applied to defect-laden models, can be cascaded, and can be combined and interleaved with other non-Boolean modeling operations.
Computing a one-to-one or injective mapping between a triangle mesh and the plane is a fundamental problem in computer graphics. Although the problem has been extensively studied in the setting of unconstrained mapping or mapping into a prescribed boundary curve, the more general case of injective mapping under arbitrary positional constraints remains an open problem. We propose a novel form of energy that allows an injective constraint-satisfying map to be recovered from a non-injective map with inverted triangles, overbound vertices, and global overlaps. The energy is equipped with theoretical guarantees, and our method performs well in practice when tested on a new and challenging benchmark.
Parametrization and mapping are key ingredients in geometry processing. When we need valid results, free of degeneracies and foldovers, good old discrete harmonic mapping is commonly used, one of the very few options with guarantees. An attractive alternative is discrete conformal mapping, which offers complementary features, free boundaries, non-convex domains, cone singularities, etc. However, no fully general and therefore reliable algorithm for that purpose was available. This is changing now. Based on recent mathematical insights, we present a sound algorithm and put a particular focus on numerics. This way, we yield efficiency and robustness, not only in theory, but in practice.
Conformal parameterization has no angular distortion.
Why does the pattern on the ear disappear?
It's due to area distortion. Let's add some cones.
There is a misalignment.
This is because cones are not flattenable and we need to add some cuts. As more cones are added to reduce distortion, more cuts will be required. There is a balance. We need to use as few cones as possible when reducing distortion. Oh, let's talk about it next time.
While looking at the photo, one may wonder how to model a textured chair like this. Now we have a deep generative network that synthesizes textured meshes with or without image guidance. First, we assign textures for different parts. Then we merge different parts that are already generated to get a whole 3D shape. And finally, we made a textured chair. Our method can generate textures for a given shape as well as randomly generate textured shapes. Welcome to our talk on TMNet.
Mathematicians naturally communicate linear algebra on the chalkboard. But on the computer, they must choose between writing in a semantically undefined language like LaTeX, and languages with well-defined semantics but notation that no longer resembles chalkboard math, such as C++, Python, or MATLAB. We introduce RHADA, a language designed to closely mimic conventional return linear algebra, and compile the source code into LaTeX, C++, Python, and MATLAB. We designed RHADA by analyzing all equations from SIGGRAPH 2019. We demonstrate RHADA by translating examples and replacing code in open source projects.
Most existing font generation models only aim to generate glyph images. We propose deep-vec font to directly synthesize vector fonts. Given a few vector glyphs as references, our model can synthesize the whole vector font automatically. Our model is designed to fully exploit the dual modality features, which are first projected into the latent style codes. Afterwards, we synthesize the text images and commands, respectively. The differentiable raster is employed to align the synthesized vector data with the images.
Converting raster line drawings to vector curves, a process called vectorization, is used daily in animation and graphic design. Unfortunately, artists often have to trace the curves manually, since modern automatic tools may fail near endpoints and junctions. To fix it, we use deep learning to extract positions of these key points, compute little crosses showing curve directions, and connect key points with curves aligned to these crosses, a novel optimization that we call polyvector flow. Come to our talk to learn more.
We introduced the first formulation for differentiable triangulations. Triangle meshes are currently the most popular surface representation because of their simplicity and flexibility. However, we cannot directly optimize over them in deep learning methods as energies defined over the discrete connectivity do not yield gradients. We solved this problem by representing soft triangle inclusion scores using Boyer diagrams. We can optimize any objective with gradient-based optimization methods. Here we optimize the triangle size to match curvature values. Come to our talk to learn more about how to directly handle meshes with deep learning frameworks using our differentiable triangulation.
Oh man, it's stuck. Dude, how'd you even get it like that? It used to look like this. I don't know, but I'm never gonna get it apart now. Well, have you considered this? Whoa, how'd you do that? The answer is repulsive surfaces. They can help you escape all kinds of tangled situations and help you design all kinds of cool things. Check out our talk to learn more.
Designing and producing multi-piece objects can be very useful in building more complex objects out of simpler parts. We want such assemblies to be easy to assemble, to support user-defined external loads, and not to fall apart whenever in use. They also need to satisfy various constraints, for example, on their shape or weight. Our framework uses efficient shape derivative computations to optimize parts in the presence of contact and friction, minimizing an objective like stress under physical and geometric constraints. We validated our results both computationally and on fabricated parts, obtaining structures that can hold loads that are more than 10 times higher compared to the initial shapes. If you want to know more, please join us for our presentation. Thank you very much.
We present a new kind of cam follower mechanisms that can exactly realize 3D trajectories specified by users. We propose a computational approach to modeling and designing these mechanisms, and verify their kinematic performance with 3D printing. By using our approach, we are able to design and 3D print a robot that can walk following a user-specified gait.